today we're going to do definite integrals, which is when we actually put limits. We call them upper and lower limits on our integral. So for this example, we fired off bottle rockets at a recent event, and the height of the rocket at any time was s of t. So we'll measure it with s, our position, or our height with s. And just so you know, the rocket was launched 2 feet off the ground. Okay, now the velocity of the rocket was v of t is 8t plus 3. And we want to know how could we find the height of the rocket at time equals 2 seconds. So I mentioned in our last video that height, the derivative of height is velocity. So if you know velocity and you want to go back to height, you would take the integral. Or in other words, the integral of velocity equals height. So in our case, we want to integrate 8t plus 3 dt. Now notice here we're going to do a t because our actual variable is a t. And when we integrate, let's see, the 8t, that's going to be 8. We keep the 8 there. The t was like a t to the power of 1. So we'll raise it 1 power, so up to 2, divide by our new power, plus 3. Now this 3 is like it's a times t to the power of 0. So 3 times t raised to the power by 1, divide by your new power, plus some unknown constant c. So we have 4t squared plus 3t plus c is my height. So s of t, again, is 4t squared plus 3t plus c. Now how do we figure out this c? Because that's not going to be very beneficial to us. What we do is we say our rocket was launched 2 feet off the ground. So that means at t equals 0, s equals 2. So in our case, we're going to say 2 is equal to 4 times 0.
Where are they, downstairs?
Okay. Squared plus 3 times 0 plus c. Or we can see from here, c equals 2. So if we put all of that together, our height at any time, t, is going to be 4t squared plus 3t plus 2. So if we want the height at 2 seconds, all we have to do is plug that in. So the height at 2 seconds is 4 times 2 squared plus 3 times 2 plus 2. Or let's see, I can do this in my head. So 2 squared is 4, times 4 is 16, plus 6 should be 22, plus 2 is 24. So at 2 seconds, our rocket is 24 feet off the ground. And so that's just kind of what we learned how to do in our last section. But now we're going to change it a little bit. What if we wanted to find out how far the rocket traveled between 1 to 3 seconds? We often in physics call this displacement if you want to see how far it traveled. So what we would have to do here is we would have to say, okay, well, what is s of 3? See how far it is at 3 seconds. Figure out how far it is at 1 second. So s of 3, we found s up above, so we'll just do 4 times 3 squared plus 3 times 3 plus 2, which is 47 feet. And at 1 second, it was at 4 times 1 squared plus 3 times 1 plus 2, and 4 plus 3 is 7 plus 2 is 9. Okay, so at 1 second is at 9 feet. At 3 seconds is at 47 feet. So the displacement amount that it was traveled, so displacement or change is going to be s of 3 minus s of 1, or 47 minus 9, which is 38 feet. So in between 1 and 3 seconds, it traveled 38 feet. So notice we wanted to do s of 3 minus s of 1. This actually happens so often that we're going to make a formula for it. So what we do is we call it the definite integral, and f, our kind switches back between the lowercase and uppercase f depending on what they're doing. So let's say f is a function we're interested in, but we only know its derivative f prime. we can use the integral to find out how much f of x changes from x equals a to x equals b. So that's what we did up above. We only knew the velocity, but we actually wanted to talk about the height, and we wanted to see how much it changed from 1 second to 3 seconds. And when we want to see how much it changes, we call it the net change. And we're going to take the integral of our derivative here. So that's what we did up above. We took the integral of the derivative, the velocity, and we evaluate it from a to b. So these are called our upper limits. And a is our lower limit. And so what you actually do is you take the integral like normal. So we went from f prime to now it's just an f. So we took the integral, and then we say we're going to evaluate it from b to a. So here, we took the integral, and we're going to evaluate from a to b. And the way that you evaluate it is you plug in the top one first, so top first, so f of b, and then you plug in the bottom one, so f of a, and you subtract them. So again, that's just what we did up here. We plugged in the 3, we plugged in the 1, and we subtracted. So let's see how this actually works. So find the integral from 2 to 5 of x squared. So to do this, first we take the actual antiderivative. So x squared, we would raise the power by 1 and divide by 3. Don't forget your plus c. And then we draw this really long line and say we're evaluating from x equals 2 to x equals 5. And so what this is we plug in the 5 first. So use some big parentheses. So we're going to do 5 cubed over 3 plus c. Now we do a minus and we plug in the lower limit. So we'll do 2 cubed over 3 plus c. Now notice what's going to happen with these c's. These c's will cancel because we have a plus c and a minus c, and they will cancel every single time. In fact, because they cancel every single time, if you know that you're evaluating it at your upper and lower limit, we'll often just kind of be lazy and not put the c in because we know it will cancel. Okay, so 5 cubed is 125 over 3 minus 8 over 3. Which gives me 39. Okay, well now what would happen? So that's basically how you do integrals with your limits. Let's just do some interesting things and figure out what would happen if, say, I switched my limits. So instead of from 2 to 5, what if I did 5 to 2? Okay. So when I differentiate, x squared is still going to be x cubed over 3 plus c. And now I'm going to evaluate it from x equals 5 to 2. So again, big parentheses, so we'll do 2 cubed over 3 plus c minus, now plug in the 5, 5 cubed over 3 plus c. And this will be equal to negative 39. So for our answer to our question, what happens if we switch the limits? If you switch the limits, the sign changes from positive to negative, or vice versa. Because all that happens is you're changing the order that you subtract them. Okay, now the more pertinent question is, well, what would happen if we break it up into pieces? Okay. So let's say instead of the integral from 2 to 5, let's do the same integral, but we're going to go from 2 to 3 in one integral and then 3 to 5 in the other integral. So let's do each one separately. So the integral from 2 to 3 of x squared dx. Again, the antiderivative is x cubed over 3 plus c. We need to evaluate it from x equals 2 to 3. So this is going to be, we plug in the top one first, 3 cubed over 3 plus c minus 2 cubed over 3 plus c. Notice, once again, our c's will cancel, and we're left with 19 over 3. Now let's do our second piece. So the integral from 3 to 5 of x squared dx. So again, our antiderivative is x cubed over 3 plus c. And we need to evaluate from x equals 3 to 5. So we plug in the top first, 5 cubed over 3 plus c, minus, and plug in our bottom, 3 cubed over 3 plus c. this will give me (98/3). Now, if I add those two pieces together, sorry, I ran out of room, so we're going to switch up here. If I add them together, we did 19/3 plus 98/3, which gives me 39. Notice that's the same answer we got up above when we did the integral from 2 to 5 of x squared dx. So it turns out you can take your integral and just split it up into pieces and you'll get the exact same answer. Now in our next one, what would happen if both of our limits of integration were the same? So again, x cubed over 3 plus c, evaluate it from x equals 2 to 2. So we're going to have 2 cubed over 3 plus c minus 2 cubed over 3 plus c, and as you might guess, every single time you're going to get 0. So if your limits of integration are the same, you will always get 0 because you're going to have something minus the exact same thing. And our example of an actual application, let's say a company knows that its expenditures are increasing about a rate. Now when you see the rate, that tells you that this is a derivative. And we want to figure out, so this is the derivative of the expenditures, and we want to see how much the total expenditures increase from year 5 to 10. So, to do that, we take the integral of the derivative, which in our case is the 1.2t plus 2.4 over t squared, dt, don't forget your t, and we want to integrate from 5 to 10. So once again, it told us that the expenditures are increasing at a rate, so that tells us that this is the rate, or this is the derivative of the expenditures. So if you know the derivative and we want to see how much the total expenditures increase from 5 to 10, we can just take the integral and evaluate it from 5 to 10. So this is going to be 1.2 t. Now this is like it's a t to the power of 1, so we'll do t squared over 2. Plus, now this is like 2.4 times t to the negative 2. So if we have negative 2 and we increase it by 1, sorry, let's keep the 2.4 there first. Okay. Now we had t to the negative 2, so if you add 1 to negative 2, you'll be at negative 1, divide by your negative 1, plus c, and we need to evaluate from t equals 5 to 10. So we're going to have 1.2 times 10 squared, we always do the top first, over 2, plus 2.4 times 10 to the negative 1 over negative 1, plus c, minus, now we plug in the 5, so 1.2 times 5 squared over 2, plus 2.4 times 5 to the negative 1 over negative 1, plus c. Again, those c's cancel. Eventually you'll get to the point where you'll stop even writing them in if you know that you're evaluating upper and lower limits. And this should give, which is 45.24. So we know that our total expenditures increased 45.24 million.